Okay, hi everyone. It's my pleasure to start this webinar and welcome you today to the special webinar on machine learning and hydrology. Today we've got Dr. Xiaoping Shen with us. Xiaoping's an associate professor with the Civil and Environmental Engineering Department at Penn State University. The interesting thing about Xiaoping is that if we look at machine learning and hydrology, most people either work with process-based models or they use machine learning techniques, but Xiaoping's one of the few leaders in hydrology who combines the state-of-the-art deep learning methods with process-based models to take advantage of the strengths of both approaches. It's really nice to have Xiaoping here today. I think Xiaoping, we've known each other for about 10 years. We've co-authored a couple of papers together. The first was our paper in water resources research in 2015 on improving the representation of hydrological processes in Earth system models. And the second paper is one with Ying Fan in Water Resources 2019 on hill slope hydrology and global change research in Earth system modeling. Xiaoping also led the special issue in Water Resources research on big data and machine learning in the water sciences. I was a little bit nervous about this special issue to begin with, because many in the science community were viewing machine learning as a panacea. However, with Xiaoping's process-based modeling background and his efforts to combine machine learning with process-based modeling, he was able to provide a balanced perspective. I want to start this seminar by thanking Xiaoping for graciously accepting our request to speak at this webinar. The webinar today will be about 45 minutes of presentation, followed by 15 minutes of question and answer. Xiaoping, we're happy and grateful to have you here today, and the floor is yours. Thank you.
Thank you very much. Thank you, Martin. Thanks for the nice introduction. It's a huge pleasure to be here. And can you see my shared screen?
Yes, it's perfect. It's not in presentation mode. It's in presentation mode now, so it's awful. It's awful.
All right. Thanks, everyone. Thanks for this opportunity. I certainly miss the days when we can actually interact in person. Now most of these talks are happening online. I hope we'll come out of this very soon. So today I'm going to be talking about what is said to be a little bit controversial topic. Is gradient descent a better modeler? I hope you guys don't crucify me for talking about this. By the end of the talk, you might find that I'm actually somewhere between full data-driven model and process-based modeling. So I'm really proposing a mixture of these two approaches. All right, so before I dive in, we do share some of our code here, and I am active on Twitter and sending new information every day, so I hope to see you there. All right, so the overall of the talk, Martin, do you think I should talk a little bit about basics about machine learning or deep learning?
Yes, definitely. Thank you.
Thank you. Then I will talk about some of the full data-driven approaches, which we just can go a long way. Yeah, and then talk about physics-informed machine learning and hydrology and how we look forward. Okay. But more importantly, I want to talk about the mindset that we have to think about this issue. Some of the things I want to convey is that once the AI figures it out, we are almost a goner. Okay, and it's very hard to compete with AI head-to-head on some optimization tasks. Also, secondly, don't assume that deep learning is not applicable to your case, whether it's because you have scarce data or your data is unobserved. For example, ecosystem, and you'll find that it's actually applicable. Yeah, it's still applicable. And we want to say there's a data synergistic effect that where a bigger data behaves very differently from a small data environment. And I want to promote the idea how to intelligently integrate physics with artificial intelligence. So what is deep learning and why deep learning? And I have this paper, review paper in 2018 on the WRR that talks about this overall idea. For supervised machine learning, mostly you're looking at this relationship from X to Y. But deep learning is essentially a brand or a rebranding of neural networks featuring very large capacity networks that have hidden layers that automatically extract features. A prototypical figure that we use here is with the traditional machine learning, you have some inputs and you have some humans to extract certain features out of that input, such as like edges or gradients, and you provide these features into a network, and that does the machine that does the classification for you. However, for deep learning, we don't have this intermediate step. We basically essentially take humans out of this loop. We go from what they call end to end. They have to go from an input directly to the output. So in place of this human, we have these intermediate layers that works with the raw data and extract the features by themselves. Okay, so think about these intermediate layers as features that are extracted from the raw data, and then they're passed on to the classifier at the later part. So along with that, you have lots of improvement in the architecture and the regularization techniques and various things that come together to make it work. Kind of the whole essence of it is to work directly with data. Okay, so you can see that the primary value proposition is the avoidance of expertise, which is very annoying to us. However, as you see on later part of this talk, that I don't think there's a exclusive relationship between expertise and machine learning. In fact, they're quite complementary. Before I dive into hydrology, I'd like to talk about this one event, which I think after 100 years from now, when we look at this moment, we're going to look at this picture as a watershed moment. This is the classic battle between Isidao and Alphago. Okay, so for those of you who understand this, who still remember this event, Isidao lost the first game, and then Garib Kasparov can't wait to come out and say, I hope he can recover, but the writing is on the wall. That's a little bit discouraging, right? But then Isidao went on and lost another 2 games. In the 4th game, he made a genius move that nobody foresaw, and it's totally genius move that basically crashed Alphago. He won the 4th game, and then he lost the 5th games, right? So that game, there was a totally ingenious move as like a talented move. But that turned out to be the only game that humans have won and will ever win against Alphago. Because later Alphago beats everyone out of the water, like 60-0, go around the table 60-0 to all the humans, and it doesn't matter what you do now, you can't defeat it, Alphago. If we look at the algorithms of Alphago, it has 2 convolutional neural networks. One is to evaluate the strength of the current position you're in, and the second is a policy network that recommends the next move. Okay, just 2 convolutional networks. Throw it with multicolor tree search, and you got AlphaGo. Okay, it's not that complex. You can implement it. So that convolutional neural network can understand very abstract concepts, and can do very, very stylized, pattern thinking. Okay, if you think so, this is a way for us to think about it, to have the right mindset. Is your problem complex? If you think your problem is complex, think about this game. Okay, so the number of atoms in the universe is said to be 10 to the 82nd order, whereas the tree search complexity of AlphaGo the Go game is 10 to the 360th power. Okay, so the game has a huge complexity, very, very complex. It's unfathomable number. But for such a complex game, this convolutional neural networks can do a very good job at analyzing the problem. So it's very abstract level thinking. So you can think about your problem, how complex your problem is compared to this one. So later on, my title actually comes from this tweet from Andrew Karpathy, who is the autopilot lead of Tesla now, but was a previous PhD at Stanford. He said, gradient descent can write code better than you. I'm sorry, because this is a very famous tweet. Essentially, if you're trying to write some code to do certain optimization tasks, and you will find that the gradient descent, which is the fundamental way that these deep learning neural networks work, they train themselves, they always come out on top. And we see on various different scenarios in hydrology as well. Okay, for deep learning, one of the things you can look at, this is in my paper, so I won't go over this, but one of the structure that I want to introduce here is this encoder. Okay, so you have lots of information coming in, but you have a bottleneck layer that is that forces the network to learn condensation. It condenses the information and then shoots back out to form the output layer, where it has to match the input. This is auto encoded, right? So think about this. When you apply for a job, you give it a one-page CV. You kind of condense your entire life into that one page of CV. And the employer, on the other hand, will reconstruct your life through that one page of CV. Or obviously, you want to put on the best highlights of your life, right? And probably hide something else, but that's one page. That's we have to really condense the information you send in. That's the purpose of this hidden layer. But after you train it, it learns how to do that dimensional reduction by itself. So it learns how to best condense that information. So to us, we ask a question: can we use this kind of structure to allow us to learn the essence of a scientific problem, right? If you can learn generic problems, what does it mean for science? All right, so now let's take a look at some of the deep learning applications in hydrology. And this is kind of the first paper that talked about LSTM in hydrology. Okay, we applied a network called LSTM, long short-term memory, to soil moisture active passive satellite. The satellite was launched in 2015, has a 2 to 3 day revisit time, and it senses top surface soil moisture. We also applied the same framework to string flow modeling, including CAMOS data set, or actually much bigger data set now that has daily data of string flow. It has accompanying attributes, and some of them have some reservoirs. And we also applied the same framework to dissolved oxygen and water temperature. So those are the case studies that we've done. Now we're expanding even beyond this. So for what is long short-term memory or time series deep learning? So right now you have architecture like transformers, GPT-3 that are more advanced than LSTM. But back in the 2016, 18, the LSTM is underneath a lot of this technology, such as Siri and Google Translate. It's essentially a self-trained, self-learned memory system that have some gates that knows what inputs that will be output, what information would be output, what information you will keep, and what information is to forget. I think about it when I walk into a classroom. A lot of information comes into my eyes. A lot of people, different faces. I need to I need to forget about 99% of all that, because otherwise my brain's gonna explode, right? With all that information. So we humans have learned the way to keep the most essential information and forget the rest. This is kind of what forget gate does, so you can act like a barrier to block some of that information. So that allowed us, this more complicated structure allows the memory to this cell state here to go on a different rail per se, to keep the memory longer. Okay, so this model is free from structural assumptions. There's very little structural assumption that's built in. It's completely driven by data. And how does it perform? Can it actually capture the hydrologic dynamics? So generically, the way this model is set up is the following. You have atmospheric forcings. You have presumably you can put in some model solutions. You can add some soil texture and some surface characteristics such as soil texture, slope, net cover, etc. And you can feed it into LSTM, and it will predict what observation you match it with. It could be soil moisture, water quality, and stream flow variables. So the first paper was in 2017. We got this paper. So essentially, we used the SMAP to train the model in 1 year, over continental United States, and we tested it in the other year. So in this year, it's completely free running with the forcing data. Right? So this is a very nice performing cell, and the top 10 percentile performing cell. It's almost capturing the solution exactly, right? So it's the blue line, which is the LSTM solution, goes through the circles, which is the SMAPS satellite, almost exactly. You look at a medium performing cell, so it start to meet some peaks, but overall this general trend was well captured. And we, over the entire continental United States, we got a anomaly correlation of higher than 0.9. So these are areas all higher than 0.9. And these you got a lower, like 0.6. Actually, these are areas where SMAP performs very poorly because it's snow dominated and also has lots of vegetation water content. So it's not supposed to do well there. If it does well, I'd be worried. So our anomaly correlation, we compared with other networks, other kinds of work, simple neural network or autoregressive functions, regularized linear regression. It has the highest correlation and also lowest error. Yeah. So another question we ask is, okay, we trained it for 1 year and tested another. How about longer simulations? Is it able to capture a longer trend? Because a lot of times we care about that non-stationarity, right? So this is what we did as a follow-up paper in 2018, where we trained the model in 3 years and projected forward in another 3 to 6 years. And we look at the trend in those projected years. We look at the sense trend that is sensed by in situ data, that's on the x-axis, and the sense trend that's predicted by the LSTM model. And you see in the intermediate time, and when there's not a strong trend, LSTM also doesn't think there's a strong trend. Where you have a drying trend, LSTM really picks it up. And in the wetting end, it kind of fall off a little bit, which is not perfect, but still, I think it's pretty good at those long-term trend. A more recent work that we looked at, we haven't published this yet, but we compared the trend captured by LSTM in 10 years going forward versus SAXMA, right? So this is Q98, this is high flow percentile, like the top 6 days in a year. Compare the trend, okay? Compare the trend changes in the trend, the observed versus the simulated. SAXMA has a correlation with the observation of 0.37, whereas LSTM has rho equal to 0.41. So that's higher than SAXMA. And looking at the low flow, SAXMA is 0.18 and LSTM is 0.53. So, and in terms of capturing that non-stationarity, it doesn't seem like that the LSTM is performing worse than this process-based model, okay, which is typically what you would assume. All right, so now going forward, we think the LSTM has this deep learning method has the potential to do a lot of the different tasks we wanted to do. For example, we wanted to make short-term forecast, not only long-term projection, but also short-term forecast. In short-term forecast, you want to simulate all the information that you can find. We normally do so by using a technique called ensemble common filtering. You run the model, you see an observation, you say, oh crap, this model is off. Now I gotta change my state and I put it down and let the model evolve again until you see another data point, and you fuse that data point in again and you put it down, and then you're always making corrections as new informations come in, right? So this is a standard ENKF. But when you do that, you have to make a lot of choices. You have to choose the covariance matrix, what to include in that covariance matrix, how to do, more importantly, how to do a bias correction. Because normally there's a correction. There's a difference between the observation and the model simulation. You have to do this bias correction. So there are a lot of dedicated choices there. People don't talk about them often. But so our thought is, okay, so if their deep learning models are so good, can you solve this problem for us? Can we dedicate this problem of assimilating information to the deep learning networks? And that's what we tried. So we sent in recent observations of discharge, and essentially we don't tell it what to do. We don't include any in covariance matrix at all. But we let the network figure out how to assimilate that information to make that projection forward, okay, for tomorrow, okay. And we call this data integration because it's not data assimilation, but it's essentially data assimilation, okay. All right, so here's some of the results. We ran this on the streamflow cases on a CAMOS data set. And if you don't do this DI, don't do this data assimilation, you get an NSE of 0.74. This is already pretty good. This is NSE. Because if you compare it to SAXMA, SAXMA is right here for the median, and SAXMA has a median of 0.62. The LSTM has around 0.74, so it's already pretty much better than SAXMA. But if you do the data simulation of the yesterday's observation, you see it's right here. So you get to 0.86. This is very high, right? This is very high. And you can look at other metrics such as low flow and high flow, and that data simulation and LSTM, both of these are much better than what SAXMA was able to produce. Okay, for low flow and high flow. The impact is much more strong with the low flow metric. All right, we can do the same thing for soil moisture in this paper, and we actually came out with an adaptive data assimilation kernel to assimilate these irregularly spaced data, okay, observations. And actually, this has seen battles. This technique. We compared it to the Koster 2017 paper, and the errors are reduced by almost 30 to 40% in this domain of the CONUS. Okay, we actually use this to predict soil moisture for the fight against the locust disaster last year.
So it has practically really helped to save food for many people. We did this for a UNFAO fellow, and he was able to save food. Whoops, I have this. Okay, actually now more recently we have come up with this multi-scale framework where you have satellite observations and also in situ observations. We train the network on both, and we are able to get correlation. This is the multi-scale model, and it's essentially can serve as like a downscaling model that downscales soil moisture observations from 36 kilometers to 9 kilometers. And this is our anomaly correlation. This is 9, about 0.8. And if you look at SMAP itself, that's around 0.6 actually. This is somewhat new. So I'm reading this right now. Oh, SMAP, it's a 0.7. Okay, so you see some noticeable corrections based on that simulation of the in situ data. Later on, we followed up with the work to actually estimate uncertainties. This is a deep learning native method called the multicolor dropout with an adiatoric term. But once you talk about adiatoric term versus epistemic, people get triggered. So we stopped talking about those two terms and we call it data noise term. Essentially, in the network, you have an item that we do not provide any supervision for, but we ask it to estimate the error because there's a way for you to propose a formula that implicitly supervises that term. So this is the term sigma x. This is a term that predicts how big the error is and what the network thinks. And we compare it with the actual the prediction error. So you see it's capturing generally the same trend. And we calculated the correlation between the predictive error and the combined uncertainty estimate. We get a correlation of 0.84. So that's not too bad, right? That's not too bad. So this is what they call the adiatoric term. There's another epistemic term that is handled by multicolor dropout. Anyway, I won't go too deep into this. And this work is here. It's talking about these different terms. So this epistemic term, or we call the network weight uncertainty term X, it's somewhat like a Gaussian process if you really look at it. Because you see the area is smaller when you're closer to the area. This is the region of your training region. So the areas are smaller when you're closer to the training region. So this is somewhat similar to a Gaussian process. But anyway, which is what you want with this term. Anyway, I'm not going to spend too much time on this. Now, let's think about the future challenges that we want to face. We don't want to say we have a network that is data-driven, so it's not applicable to areas in the world where you don't have data, right? Where you don't have an extensive data set. So we have come up with different solutions for those problems. For one kind of problem, you have a few gauging stations somewhere. This is particularly true for like places like China or South America. Okay, you have a few gauging stations. You have maybe a couple of years of observations. In that case, this transfer learning technique is very achievable, So with the transfer learning technique, you train the model over camels, over an extensively sampled area. Then you take this model, you fine tune it elsewhere. And then also you can also keep some of that weights constant, right? You can freeze the weights. And essentially it's like once you learn how to play the cello, you can learn to play violin rather quickly, right? So it's because these tasks have similarities. You don't have to learn everything from scratch. Okay, so when we're comparing the models that were done using transfer learning, so these are that model versus this box comes from a local training model. Okay, so you only use the data locally to train that model. So as we can see, when you have only 1 year of local data, that transfer learning model is noticeably better than this one. And that is true for the China data set, for the Chile data set. So there's a huge difference. The NSE went from 0.64 to somewhere like 0.72. That's a huge difference, right? And also, you can also see that with the CHEMOS Great Britain data set. So this GB data set already has an extensive set, but throw in the CHEMOS transfer learning data set, it's still able to improve that just a little bit, okay, just a little bit. And if you have 4 years of local training data, you still see that benefit. You still see that benefit. Okay, so albeit not as pronounced as this case. All right, so there you go. This is a way way of taking advantage of data on another planet, on another continent, to actually improve your model in a more relatively data scarce region. Right? What about areas where you don't have data at all? So this is what we call prediction on ungorged regions. So let's think about this whole region that doesn't have any gauges. This is different from the prediction in ungorged basins. So when people do PUB, they randomly hold out some sites. So when you do that, you always have a representation from your neighbor, right? So maybe your neighbor is in the training data. But in PUR, you don't have any neighbors. It's like driving blind. Okay, so it's like in this entire region, there's not even a single gauging station. So that's very, very risky, right? You think about it. And we tried that experiment. So we trained this model in 6 out of the 7 regions and tested on the 3rd. The question is, should we trust that the model would give us a PUB like performance of 0.69? This is what Kranzer et al. gave for PUB. And we proposed some mitigation measures. The conclusion is that you cannot. Okay, so when you jump, when you have a region, entire region like that, if you don't have any data, the performance went from over the CONUS went from 0.74 to like less than 0.6. So it's a 0.54. So there's a noticeable dip in the performance because of this region is not represented. However, there are some techniques to mitigate that. We try to include soil moisture active SMAP data as an input, and we also proposed a method called input selection ensembles. Basically, this is to say that some of these attributes are overfitted, but if you have 3 different models with different input options, they all are wrong, but they're wrong in different ways. And you take their ensemble, the ensemble tends to be better than each one of them. Okay, so if you look at this black box, that is the ensemble. So it turned out that it's better than this one. So in other words, you can get to around like 0.58 of, I can't remember the exact number, 0.58-ish with this ensemble network. So it turns out that if you have an FST model that's trained in an area, that's the best, but it's better than the PUB, which is randomly select code out. This is better than PUB plus FDC. If you have flow duration curves, you can assimilate those flow duration curves. These two are kind of equal, okay, it's, approximately equal. So I change the sign here. It's kind of equal to the process-based models that are trained and calibrated in a basin. Okay, and both of them are better than the PUR, or the PUR scenario. All right, so it seems like the deep learning is even applicable, and it's not the worst choice. It's actually the best choice, at least among the ones that we've found, in a region that doesn't have any gauges at all. Okay, 28 minutes. Then the next question is, can machine learning handle human influences? This paper is about to be accepted. It's a minor review. So we trained a 3,000 basin data set, and where we look at the different gauges and different reservoirs. The reservoirs, you know the type, some are flat control, some fish pound, some are hydroelectric, some are irrigation dams. So we look at all that. We find that the model can do a very good job when you have a degree of regulation that's pretty much a metric of how much water you can store. If that degree of regulation is less than 0.1, it's less than or equal to 0.1, that's about like a month of water. Okay, the reservoir can store about a month of water. Then the NSC is right here. It's like 0.72-ish to 0.8. Okay, that's very nice. Actually, the basins with reservoirs, they behave better than those without reservoirs. And I think about this, the reservoirs somewhat serves as the purpose of like a storage, like a buffer, right? So it makes it easier to predict. But as the reservoirs gets larger and it's able to modulate, regulate across seasons, then the performance starts to go down because the model actually cannot fully anticipate these large reservoirs, how they operate. But for the small reservoirs, they do very well. They do very well. That also means that in a basin with hundreds of smaller reservoirs, you can lump all the smaller reservoirs into one. And that greatly simplifies how we do this hydrological modeling, right? How greatly simplifies that. Okay, so that means we do this kind of implicit modeling of all the smaller reservoirs, and we focus on a few of those large reservoirs for special treatment. Okay, and also in this study we also showed that the basins with reservoirs, they behave characteristically different from the basins without reservoirs. So if you train the model without the reservoirs, you will get awfully wrong in the areas with reservoirs. So they behave very differently. They also draws us to our attention that in the traditional hydrologic modeling, you cannot ignore those reservoirs. They are there and they play an impact, even if they're small. Okay. Later on, some simultaneous work also expanded this work to dissolved oxygen, stream temperature. This is a paper in the ERL. This is in ESMT. There's a paper. This paper actually, the LS team works perfectly. It's like a wonder. It's like works wonders for stream temperature. The NSE, is above 0.975. And I was asking my students, hey, are you sure about this? Can you check this? So he checked it many times, and he was able to reproduce results, and it seems to be valid, right? So compared to an ARX two-stage autoregressive function model with the exogenous input, it gets an NSE of 0.94. That's not bad, but there's a material difference between these two. And we were able to get the RMSE to be around 0.7 degrees. Normally, you see in the literature they're right around here, 1.3 to 1.5. Okay, so that's a very noticeable difference. Okay, so now I want to talk about the effect, the idea of data synergy. The data synergy refers to the fact that if you train models on different domains and combine them together, you get a better model. So typically in the past, we think of elementary statistics. You want to divide the population into different beings, different regimes, and fit a small equation in each one of these beings, right? And that's kind of always how we do this. But now with the deep learning, you don't have to do that division. In fact, you can, we compared the global model, which is this blue box, with the red model, with the red box, which is the local model. The global model every single time beats the local model, okay? So then you might say, hey, might be because you have more data, simply have more data point in the global model. And so we run analysis where we have the same amount of data points by downsampling, right? Same number of data points. We find that for the correlation, the regions with more diverse training sets, if you train it with a couple of diverse diverse training regions, the model turned out to be more robust than if we trained it locally or with a more homogeneous data set. Okay, so this is a very nice message. It says that actually deep learning, it wants more heterogeneous training data. It wants to see more differences, and it can leverage that differences, right? And this effect we call it the data synergy. Okay, and this is under review right now. We think that the machine learning is able to solve some of the hydrologist nemesis, including the parameter non-uniqueness, such as that leads to equifinality issues. It can solve multiscale modeling. We've just demonstrated multiscale modeling. There's some other contexts where this is important, and it can resolve human influences, including the dams, right? So you don't have to specify every rule sets for how a reservoir operates. In fact, for thousands of dams, you can't do that. But with machine learning, there's a simple and uniform solution to that problem. So now I'm going to talk a little about this parameter uniqueness problem. And this gets into the concept of physics-informed machine learning, or I would call it differently, but right now let's go with that term. Yeah, a lot of times because hydrology interact with other ecosystems such as geochemistry systems, there are many variables we cannot observe, such as evapotranspiration, groundwater, deeper soil moisture. These states, you can't observe them, but they're important for ecosystem, right? They're important for various different purposes. So what about them? Is that the real limit of machine learning? And we think that machine learning is still applicable in this case because we can combine the full might of machine learning with process-based models. Okay, we're proposing a framework called preemptive learning. Okay, we call this differentiable preemptive learning. In this essence, we have built a circuit model and we wrap it inside our machine learning framework. This machine learning framework essentially can estimate the parameters for that process-based model And then utilizing that, it's able to predict all the things that this process-based model is able to predict. Okay, and it's able to, this comes out to be like an end-to-end framework that is trained based on the output of that observation, and you can match it with the output of that model, and you match it with the observation. Okay, we calibrate the big hydrological model. Actually, we calibrate other models too, using SMAP data, and we calibrate it to stream flow data as well, and the LSTM based DPL scheme. Okay, so here, imagine this is SMAP grid. Okay, so we take an 8x8 patch. We take one grid cell from that 8x8 patch, that as the training set. So we call this S8. So S8 is one grid cell out of every 8x8 patch, and we can evaluate, and we train the network that way. So it predicts parameters, right? So predict parameters for every one of them. We can evaluate based on this grid cell or based on the grid cell in a nearby grid cell. Okay, so it's a spatial extrapolation. So we compared our results with the shuffle complex evolutionary algorithm. The SU is a standard algorithm. It's we kind of understand it. Okay, you have some other better algorithms, but they're not orders of magnitude different. So we compared that with this dashed line. So it gets below this performance threshold 0.05 in around 1,000 epochs. Of 7 parameters. That's kind of what you expect. However, when we look at this calibration of S16, so that's 1 out of 16 by 16 patch, it gets below that threshold in about like 350 epochs. And then later on kind of start to kind of flatten here. Actually, the ending metrics is not as good as SUA. But if you look at S8, it gets down here below 35 epochs. And look at S4, that's 1 out of every 4x4 patch, this gets down to here in 5 epochs. And the ending metrics is also better. So, okay, so interestingly, there is this scaling impact coming from more data, right? Apparently the scaling effect. Overall, if you look at S8, it saves about 4 orders of magnitude in computation. Normally for such a dense calibration, you need a supercomputer with 100 processors to run it to 2 to 3 days. With our DPL scheme, we need only 1 GPU and calibrate it for 40 minutes. Okay, so that's a huge difference. Now it's capable of modeling other variables. Okay, so we also compare it in terms of spatial extrapolation. Okay, so this is evaluated on the neighbor. You notice that SCUA has a notice bump up in that error, whereas so this is the training sites. This is the neighbor test site. Okay, so going from here to here, you notice that this SCUA has a bump up in the error. Whereas for our 2 schemes, both of these are our DPL schemes, you almost don't notice any changes, right? So it's flat. That means it's spatially the spatial generalization is better. And we look at the variable evapotranspiration, which is not included. Okay, this is not included in the training. The training doesn't see this at all. And we see that with the SCUA, we compare with the MODIS data, you have a calibration NSC of 0.36, correlation 0.78. But the DPL has a correlation of 0.75 and NSC of 0.55. Noticeably, the error is the bias is much smaller. Okay, so we can see that this DPL get the good results for the right reason, because everything is now more coherent. Okay, and if you see the parameter fields, you start to understand why. So this is what the SCU gives you. This is what the DPL gives you. DPL gives you a spatially coherent data set. That's what you expect to see for this VIC model. Okay? It's dependent on the moisture state. Whereas for SCUA, it gives you all this jungle mix because of this very famous problem of equifinality known in hydrology, right? So your different parameters can give you the same ending outcome. So you can take a very random place in the parameter space and then you distort the other parameters to fit it. So you get a jumbled mess. Okay, so this is much more physically coherent. And we compare with different cases where streamflow cases where you have our VIC model calibrated against the streamflow. Okay, we compare that with the multiscale parameter regionalization scheme, where here they got an NSC of about 0.32 for VIC, we got, and this is based on the Fortran-Baker model. We fit the parameters to the Fortran-Baker model. Okay, we got around 0.46. Okay, 46. So there's a very noticeable jump here between these two curves. And we also compared our scheme for a global headwater data set. And this is actually spatial extrapolation. This is a prediction on ungorged basins. Okay, so the Beck et al. 2020, they got an NSC of around 0.46, which is already pretty good. But we can go to 0.58. Okay, so, and this is before you do even routing, anything like that. So this scheme has beaten the regionalization schemes. I can say that. And more importantly, let me see, what is my time? I have 5 more minutes. More noticeably, we note the scaling impact. Okay, the scaling impact. This curve takes a little bit of brain power to break through. What I'm trying to demonstrate here is going from S16 to S4. When you have more data, we look at this. The ending metrics gets better. Okay, this is the ending metric. This difference is not large. You shouldn't expect this to be large because we're talking about the ending metrics here, ending error here. So it's a very small range, right? But you see, as you go for more data, the ending metrics gets a little better. We look at SCUA, it also does this, but it's on a much higher level. Its layer is much larger overall. It's, and then if we look at the neighbors, okay, the neighbors, this is extrapolation. Okay, this is, sorry, the red lines are extrapolation. This green line is the ending metrics, okay? This is spatial extrapolation. And we look at the uncalibrated variable, this is ET, okay? The ET, it becomes the correlation, okay, so it's higher the better. The correlations become better as you have more data. And then we look at the epochs, though. The epochs that it takes to go below that behavioral threshold, it went from 300 to 30 to 5. So we see this beneficial scaling impact. Because when you train these models in a machine learning framework, they learn from each other, okay? Think about here in the Midwest, if we know how to fix my house here, I pretty much know how to fix my neighbor's house. It's a similar task, right? It's a similar task. So I learned to do this task. It's a similar thing to that task. I learned experiences across these different sites. It gives me this economy of scale, like kind of effect. Okay, so the economy of scale says if you more data points, the cost per data point per training site becomes smaller. That's exactly what we see with this blue little curve. It's a pretty dramatic change. However, we also have this kind of network effect, effect, because everybody now gets better service because everybody now has smaller errors. So this is really an impact that says you need to exploit this. You need to ride this scaling curve up. You need to bring all the data together and harness that power. Okay, we tried that experiments with the stream flow as well. We varied the amount of basins we use for training, going from 0% or maybe 2% to 100%. Okay, we see this initial very rapid phase of improvement in the KGE. This goes from 0.444 to 0.56. So we think that in this phase, the model is really learning what the problem it is working on. It's trying to master that problem. As you give it more data, it's able to do that. As to this phase, it started to go up much more slowly and asymptotically. I think that is because it's doing fine tuning at that phase, okay? Because you have more spatial proximity, and this is where Beck 20 is. The Beck 20 scheme, it's 100% data, and the performance is here. So if you think this curve for Beck 20 is monotonous, then it's fair to say, and you guys can criticize me if you don't agree with this, that we can achieve the same results using only 12% of the data. Okay, so there's a lot of data efficiency there. Okay, so later on we have done more work, but I'm gonna just kind of skip this. We have been able to do add routing schemes that we are now able to simulate larger basins, connecting these smaller basins. We have now have a multi-scale model that I mentioned earlier that can simulate, can use both in situ and satellite data, and I can actually have, this is the state-of-the-art simulation of soil moisture at high resolution. So we see that come back and think about all this whole thing. Okay? Stand on zoom out a little bit. We look at the process-based models. The process-based models, what are the advantages and pros and cons of each of these? But the process-based models are built from the bottom up to observe emergent patterns. We hope what we put into these models, or I hope we know what we put into these models. We can run experiments and we can identify the causal relationships. We can assess those relationships. But there's severe limitations as well. The number one limitation is the human bias. A lot of times people choosing a model because it's what the school of thought was doing, right? The parameter calibration is a whole mess, as I've demonstrated, and there are things that we don't know, and these errors, they compound and making each other more complex, making it really hard to diagnose what the problem is. For big data machine learning, it's built from the top down, so always tend out to be more accurate. It's almost always the case. It's really hard to fight against it. It's less biased because it doesn't have ego, right? It doesn't have ego. It could have the things to identify things that we don't know, that there's an opportunity, and it's highly, highly efficient in computation. But the limitations are it can't observe everything. It might be very difficult to interpret, okay? And it may not fully respect physical laws, which is very annoying to us. And it does not understand causal relationships. So it can get tricked by associative relationships. So I think there's a synergy between them. And that's what the current frontier of the research, which is which is to link the two. And parameter learning is like a step into that direction. And so where we go from here, we think that hydrologic deep learning has launched a full-on assault to offer a full suite of services with high accuracy and low cost. Time series deep learning will spread over to other domains it has already for water quality. Deep learning will not replace process-based models. On the contrary, there will be a class of unified models that link the two together. Deep learning will be deeply ingrained into next generation models for science and practical operations. And this is something I wrote in 2018, okay? Perhaps one day deep learning will become an inalienable component of the hydrologic discipline itself. I'm going to skip this slide, which talks about landslide, which is not a part of the work that I do. And, I'm going to end here. This time now, 47. So I'm going to end here for discussion. Thank you.
Thank you, Salpen. That was a very informative presentation. We'll be now moving towards a question and answer session. So the first question is from Kasra, and he's asking, for the data space reasons, there was one slide that you showed, how objectively do we select the data from different places to train our models?
In that scenario, we don't really select data. We use all the data that we have to train the model. And that's always what we prefer to do, is to use all the data we have. And there are maybe a few cases where that's not optimal, but that's at least that should be the first choice.
The other question is from Raymond. So he's asking, I think you mentioned in one slide where you said you don't prefer it to call the physics-informed neural network or deep learning method. So what would you call it?
I have some candidate ideas, differentiable hydrology, or knowledge discovery networks, et cetera, but I've yet to come to one term. I think that we'll have to have a few people in the community to come together, because otherwise, if it's something that I come up myself, maybe other people may not agree. So we might some community consensus here, but I think maybe differentiable hydrology would be a good term.
The next question is from Saman Razavi, and he says, nice presentation. I understand that getting higher NAC is a good thing, and nice that neural networks can achieve that. But wondering if you could comment on how it can help us advance our understanding of hydrology. For example, the benefit to real-time forecasting is pretty clear, but it is not as clear for other possible purposes of modeling, example, hypothesis testing. And he said, great talk.
Oh, okay, so I saw that. Okay, thanks, good question. I think there are obviously different objectives. There are some people just care about making the predictions better, and in the real world, that's what people use to get better results. But to improve our understanding, I think that the integrated process-based learning and neural networks, that would be a good frontier to pursue. And I also think that, so that there are ways for us to really update our knowledge in this approach. For example, I'll give you one example. So for this large-scale modeling work, what we're trying to do is actually not just making this framework work for larger basins. We're actually trying to learn about hydraulic geometries of this network. We think that it seems like some of the parameters, such as Mannion's roughness coefficient or what is this? Some of the parameters in the hydraulic geometry relationships, they're actually learnable by this physics-informed machine learning. We're actually able to learn those parameters. So that advances our understanding of the system, and then you can look at the relationships between the learnable things versus the relationships that predicts these learnable things, right? And then you could, you know, a while ago in 2018, have another paper that I talk about alternative pathway. That's also a possible pathway where you can actually build a model, train it with lots of data, so that you know you have a very good model. Then you can apply these techniques called interpretive AI techniques that can you know, decomposes what the model has learned. You can look at the gradients and you compare it with your common sense and see if they make sense, right? So, and if we find something new, maybe we think about maybe this guy's got something. Maybe this this robot's got something here, so we can better investigate those relationships. So there are multiple paths to take, and I think there's a whole domain of knowledge that we can go. There are so many assumptions we have used in our models, and we can, you know, check them out again.
Yeah, thanks. So there's another question from Rajesh, and I also had one question, and they are both very similar type of questions, so maybe you can answer both. For me, I was going to ask if you could talk more about the predictive capability of the deep learning methods for known unknowns and unknown unknowns. And Rajesh's question is, considering the non-stationarity, how feasible are deep learning methods for projecting future climate change when the model is trained on historical data?
Sorry, I don't see this question. Is it on here or it's not on the chat?
It's in the chat, so that's why. So considering the non-stationarity, how feasible are deep learning methods for projecting future climate change when the model is trained on historical data?
You know, that's a very good question, and many people are concerned about that. I think it's a legitimate concern, and that's why we shouldn't trust it blindly and should evaluate it very thoroughly before we start to utilize it for real-world purposes, right? And that's what we did. But what we found is you cannot discount it without any, like, we shouldn't assume it to be better, but we also shouldn't assume it will be worse. In fact, if you look at this, we were looking to predict future trends. It didn't seem like that LSTM is worse than a process-based model like SAXMO. Okay, so that's number one. Secondly, there's a paper that's published by Duan et al., and you can check out this paper. So they look at the input-output response relationships under extreme scenarios. So they flush the model with incredible amount of rainfall, and they think that the model, the LSTM model, was actually the machine learning model was able to give sensible extrapolation that looks plausible. You know, it wasn't going crazy, right? And I think we need to evaluate it thoroughly. And so far, I actually haven't seen a case where the machine learning is worse than the process-based model in terms of future trend predictions. And I can very easily, if we find such a case, I very easily accept it. I won't say, okay, I'm defending this versus the other. We can just be more evidence-based. But one way to think about this is, although your climate is changing, let's say, well, I'm in Pennsylvania. If I get warmer, I become more like Virginia, right? But the Virginia is already in your training data set, right? So in a way, this is a way of doing what is known early in hydrology known as space for time, right? So as we change, we become more like our neighbors. but your neighbors are already in the data set. Unless you're talking about the very frontiers, such as the Arctic areas or the tropics, the boundary cases. There may not be neighbors to look into, right? For example, even the Arctics, as it greens up, it becomes less Arctic, right? So you might already have data for the less Arctic scenarios. So that means a lot of these climate change are not out of the realms of machine learning models. And at least I think what the attitude we should have is not assume a priori that one is going to be worse than the other. And we look at, let's use some actual results to see what it is.
Okay, thanks. Another comment from Bowen Zhao. So nice presentation. Have you tried to combine process-based models with data-driven model by replacing those processes in process-based models that are commonly described by empirical equations? Because many empirical equations were also gained from data fitting at the very beginning. I'm wondering if this can improve the performance of both modeling options.
I think that's a wonderful idea. And we're trying that with some ongoing work right now. We're trying exactly that. And, that if there's interest, there's certainly opportunities that we can people can work together with or without me, either way it's fine, to look into these. I think that there are a lot of opportunities there.
Thanks. Another comment from Hong Jeng-hu. What is typical computational time, hours, days, using a regular PC? So it may be referring to some of the computations that you are doing.
Okay, yeah. So if you're training something like LSTM, I mean, there's a variability, right? It depends on how optimized that model code is, and it makes a lot of difference. So we were able to leverage a very efficient code. So at the core, we leverage the cuDNN library. And if you compare this, with some of the other code, that the cuDNN version allowed us to train on the CAMOS data set for 10 years of training data. We train it 300 epochs to convergence. That can be done under an hour, okay, on a GPU. So when you train these networks, you don't use CPU, you use GPU. Under an hour, you can train it. And I noticed some of the other code, it could take, those other code could take you 10 to 20 hours. So the efficiency varies a lot based on whether you're utilizing a very efficient code. But if you make an inference, that's extremely trivial. Okay, if you make an inference over the entire United States, it takes you probably under a minute time.
Thanks. And probably it would be the last comment question because of the time limit. It's from Brian Tolson, and he says, convince me the computational times are equivalent between SC calibrated weak model and deep learning calibrated weak model. That was not clear. Example, what is an epoch in context of SC?
Hi, Brian. Nice to talk to you. So yes, an epoch in our definition is really not an epoch. It's basically on average one forward run per site. Okay, one forward run per site. That's essentially what we mean by an epoch. So essentially you're talking about how many forward runs you have run on average for each grid cell here. And both of them here are using the same model. They're using the same model. Okay, so between SCUA and this DPL scheme, it's not 4 times faster. It's you can think about it. There's 100 epoch, there's 1,000 epoch here versus 300 or 35 or 5, depending on what sampling density you have. So what I mentioned here by 4 orders of magnitude is compared to like a CPU version that you calibrate on a supercomputer. So both of these are actually using a faster surrogate model.
Thanks. I think we'll have one last question from Martin.
Yeah, thanks, Xiaopeng. That was a wonderful talk. I really appreciate you taking the time to give it. I had a final question or comment, maybe, based on some of the comments that Saman made. And my perspective in hydrology is that hydrologists have been using machine learning more for fitting than learning. And it seems as if some of your work is beginning to get to the learning aspect. And some of this was beginning to come through where we look at statistical predictions from yesteryear, and people were concerned about the difference between association and causation and needing to have physical evidence to back up the statistical predictions. And it really seems as the work that you're doing with your parameter estimation and hydraulic geometry work is really beginning to get to the learning aspect of deep learning. And I really appreciate that, and wondering if in your final comments you can comment on that a little bit and talk about what we might be able to learn. Like, can we learn data transfer functions? What can we learn from the data? In order to push the marriage of machine learning and process-based modeling forward in a more effective way?
Exactly. I totally agree with that. I think that's a very good summary. It's better than my summary. We think we can really shift our focus from curve fitting to learning, right? So we're using the machine learning as a teacher to teach us how various parts of this problem. And the really critical thing here is this teacher is very strong, but he's not very good at explanation. So you have to ask the right question. You have to pose a very concise, very precise question, so it answers your question precisely. And that's what we're trying to do with parameter learning, with also in the future might not be parameter learning, might be process learning, right? You can learn various different things, and all this, you can interpret this in cooperation of process-based model with machine learning as a way of adding more constraint, as a way of more precisely posing that question, right?
Excellent. Well, thanks again, Xiaoping, for giving this webinar. It was very instructive for many of us, I'm sure. And Praveen, you want
Thanks
to
for the invitation.
Any last words?
Yeah, I just wanted to say thanks again to Xiaoping for the talk, and I also want to thank everyone who attended this webinar. Just note that the video recording of today's webinar will be available later today in Core Modeling website. And just a reminder that next week we'll be having Professor Martin Clark from the University of Saskatchewan, who will be talking about numerical issues in land models. So please stay tuned. That will be all for today. Thank you again. Please stay safe.
Okay, thanks everyone. Okay, bye-bye.